Alright, so our last video was on how to go from position versus time here to a velocity graph. This time I want to take a look at how we actually go from velocity to position. And again, we use kind of some of the similar principles, just backwards. Okay, actually, what we're doing here is very simple calculus. Okay, to go from velocity to position, we take the integral. To go from position to velocity, we take the derivative. We're taking some shortcuts and, very simply put, finding areas or finding slopes like we did last time. Okay, so we have looked at velocity and time, and we know from some of our previous work that the distance an object travels is velocity times time. So going off of that principle, if I take the velocity an object's traveling, -1 meters per second, times the time, 2 seconds, I'll be able to figure out how far it's traveled in this period of time and then be able to take it down to my graph. Position versus time. So what I typically do is I make boxes. Again, the bottom of your box will always be your origin or your zero on the axis, your x-axis. And then I just want to know what the area of this box is, because again, essentially the area of this box is the distance the objects travel. We'll put that down on paper because I think that's important to have in your notes. The area under a v versus t graph, well, that's distance because that's velocity times time. Okay, so the area here, -1 meters per second times 2 seconds, gives me -2 meters. So for these first 2 seconds now, I'm going to drop this down, and I need to travel -2 meters. Now, if you notice, when I go ahead and just start my graphs or get them set for me to translate from one to the next, I always draw the graph I'm translating to so that I could go both positive and negative, because I don't know if I'm going to need the negative or not, so I might as well draw it. Here we are, -2 meters. Now again, most people start at origin, and I think that's the natural thing to do. You could start somewhere on your x-axis if you like, but again, I start at origin. I think it's just the most simple. So you can do wherever you want as long as you're not told otherwise. I'm going to set my scale, so I need -2 meters. I'm going to go ahead and just say -1, -2, -3, -4. Okay, and then up here I'll go ahead and do the opposite. 1, 2, 3, +4 meters. So I know -2 meters in the first 2 seconds. So I'm going to drop this down, and I should have, at 2 seconds, my object has gone -2 meters. Okay, now I'm going to go to this middle section here, and again, we've learned that this line here, okay, is on the x-axis. That means that from 2 to 4 seconds, the object has a velocity of 0, which means the object is not moving. So think of it that way. As time is moving on, we're at 3 seconds now, and 4 seconds, the object hasn't moved. So if you have a velocity of 0, we need to create a line that shows a slope of 0. Okay, and then the last portion here again, oh no, I don't have a box. So what I need to do is actually just pretend that it is a box there. Okay, and then we can find the area again using the same principles. So this time my velocity looks like is 1/2 meter per second, 0.5. I'm going to multiply that times the amount of time I'm traveling. 2 seconds, 4, 5, 6, so 2 seconds, and that's going to give me 1 meter. Okay, so now I need to get back 1 meter, 1 positive meter, when I get to 6 seconds. And so that would look something like this. Okay, now you can actually check your work, because we know the slope of these lines should represent the velocities of these lines. And so real quick, I'm just going to go, so rise over run, -2 divided by 2 seconds, I should have -1. Check. Here, slope of 0 means I'm not moving, so that's a velocity of 0. Got it? And then this last portion here, rise over run, I go +1, a run of 2. 1 over 2 is 1/2, so I should be going 1/2 meter per second. Check. There's just an overview of how to translate from v versus t to x versus t.